So this year I learned calculus, and it starts off pretty easy. We're just learning the slope, which is something we learn in algebra. It's just the change in output over the change in input. But in calculus, something weird happens. The change in input is so small it's practically zero, very close. When we take the slope with this change in input, we get the slope of a point, or the tangent line, or what most people call the derivative. And once we learn the derivative, we can start to learn these different formulas, these different tricks, these theorems that help us unlock the secrets of calculus. We were in the middle of doing this when we were interrupted by a 3-day field trip. I know what I was going to learn when we came back. So, what did I miss in math class?
Well, you missed the fundamental theorem of calculus.
I climbed into a tree, I sat and stared into the distance thoughtfully. See, I barely understood integrals, so I'd have to start with learning them. I knew calculus is all about looking at what happens to an output when one makes a very tiny change to the input. I learned about how this applies to derivatives, but how would it work with integrals? That's when inspiration struck. I looked into the stump of a tree branch and looked at the rings that make up a circle. I thought about the many rings that form this area, and that's when I came up with a plan. Each of these rings has an area that is negligible, so we can just look at the circumference of the rings, then add them all up to find the area of the circle. Next we're going to plot each of the circumferences, then draw a line of best fit to represent every radius in the circle. When we fill in the area of the triangle, this represents all the circumferences that we've found. Now we're simply working with the area of a triangle, where the base is equal to 4 centimeters and the height is equal to 8 pi centimeters. When we plug our values into the triangle equation, we find the area is equal to 16 pi, which is equal to the area you'd get from pi r squared in a circle. The function we use to find the circumferences is going to be c of r. We multiply that each time by a tiny change dr to find the increase in area. We did that from the radius of 0 to the radius of 4, and took the summation of all these tiny changes to find the integral. The derivative looks at what happens to the output when there's a very tiny change in the input. Let's say we took the derivative of the integral. We quickly see that the tiny change in radius, dr, cancels out, which leaves us with the change in output, the area. This is the fundamental theorem of calculus, and it makes sense if we look back at our circle example. If we make a tiny change in dr, the output function, the area, changes by dr times the circumference, c of r, and we get this new triangle with an additional dr. The fundamental theorem of calculus gets its name for a reason. It connects the two main calculuses, integral calculus and derivative calculus. Using the fundamental theorem, we can understand anti-differentiation. Before computers, we need to measure the definite integral using thousands of tiny approximations. However, with anti-differentiation, it takes a fraction of the time and work. Additionally, the fundamental theorem helps us gain a greater understanding of rates, such as velocity and temperature. Calculus helps us understand nature, our world, and the fundamental theorem helps us understand calculus.